Okay, so hi and welcome to video notes 5.5 on direct and inverse variation. So in this one, we're going to kind of talk about a form of a linear function, meaning that this is some version of it. We've got lots of different ways to look at linear functions, and this is one of the ones that we're going to open with. So let's get right into looking at what direct variation is, and then we'll come back and look at inverse variation. So a direct variation is an equation of the form I'm going to write it above because there's not enough space. So f of x, or our output, is equal to some constant of variation times our input. That's it. There's not a lot to it. It has an input, and it has an output, and it's got a constant, meaning that there's some value that's always there. If you're paying attention, you might even recognize this because you have a little bit of information about linear functions at this point. You can kind of consider it as slope, if you will, some value that's always multiplied by x that provides that constant rate of change. And that's all a direct variation is. It's kind of like a simple form of a linear function. K can never be equal to 0 because otherwise you don't have much of a function. We do call k the constant of variation. In doing that, we like to say that in this direct variation, we like to say that y, or f of x, in our case, f of x varies directly with x. Okay, meaning that what happens to our output directly happens to our input. Or vice versa, we can even write the reverse because it's also true. So x varies directly with f of x or y. Okay, which means to you that if I increase x, right, if I make it go up, then y also goes up. So as our input goes up, our output goes up. And vice versa, if the input goes down, the output goes down. So they're in a direct variation. As one changes, the other one changes the exact same way. So here's some examples of what direct variation may look like. F of x equals 1x, f of x equals 2 times x, and these are of course multiplied because they're kind of like slopes, right? They are slopes. F of x equals 1/2 x, it could be negative 2x, it can be negative 1/2, it could be pi if you wanted it to be. So, and these are all your k's. Right? There's your constant of variation. That's the value right directly in front of your input x. Okay? And that's all a direct variation is. Notice there's nothing added or subtracted to the back side of these. It's quite literally a constant, an input, and an output. Not much more than that. If we take one, just really quickly, we'll take a look at this. If we take this direct variation of f of x equals negative 3x, you'll notice that we can use, remember when we did literal equations? Basically formulas where we pushed around the numbers and moved them. If we take f of x equals negative 3x and we divide by x, it could look like this. It may come in this form, or it could come in terms of having a y over there too. These are all the same. These are all equal. In this one we exchanged f of x for y, and we solve for x, right, by dividing that 3 over. It could look like that. We could also divide the x over and have it solve for the constant. All of those are different versions of this exact same direct variation. Just to let you know, we can push them around. They will look a little bit different from this from time to time. So let's explore what's going on with a direct variation. So we're going to take this one here, the direct variation of f of x equals 2x. We're going to put it in our evaluation table, and we're going to put some inputs in. And let's see what happens. So if I take 1 and I plug it in for my function as my input, so f of 1, and I plug 1 in here, 2 times 1 is 2. Pretty simple. So f of x, then our output is 2. Well, let's go ahead and plug 2 in there. I'm pretty sure you can do this in your head as well. F of 2 then is 2 times 2, or 4. But let's take a peek at what's actually happening here, and I want to draw attention to this. As we double the input, so going from 1 to 2 is technically doubling, so we're doubling the input, and then our direct variation says that whatever happens to the x input, it's directly related to what happens to the y input. Look what's happening with the y. It's doubling. We doubled it. We're not taking the difference. We've done differences where we subtract the 2. It would happen to be 2, but that's not the same thing. We're looking at the ratio of how we change between inputs, and that same ratio, that same change, should happen between the outputs. A little different look at this. Let's try another one to see if we can highlight this a little bit better. So now we're going to take the function f of x equals negative 3x. Let me switch my color here real quick. So if I input 1 here, f of 1, negative 1, or I'm sorry, negative 3 times 1 is negative 3, so our output is negative 3. Let's go ahead and plug in 2 and see what happens again here. What we should see, because this is a doubling from 1 to 2, is a doubling of our inputs, we should see a doubling here, right? So we can always kind of already expect what's going to happen. So let's plug it in and find out. F of 2 going in here, so we're going to get negative 3 times 2 is going to be negative 6. We get negative 6 out. It did double. 3 to negative 6 did double, just like it did over here for this direct variation. Doubling our input, doubled our output. So what happens if we go the other way instead of doubling? What happens if we take and let's divide this by 3? Let's cut our input in thirds, right? So we're going to cut it in thirds. So let's plug in f of 1/3. And negative 3 times 1/3 is going to be negative 1. So on our input, so now I'm going to grab my green pen. I've been waiting to draw this for a second. So this here, we doubled, and we saw that they doubled as outputs over here. So let's look at what happens when we cut it in a third as for x. What happens over here? Well, we also cut that in a third, or you can say multiply by 1/3 or divide by 3, basically the same thing with maybe division of 3 looks a little better for what we're doing. So if we divide it by 3 over here as our inputs, 1 to 1/3, right? That's the proportion. We're dividing it by 3. Then look what happens to our output. Negative 3 becomes negative 1, and that's divided by a third, or divided by 3, not divided by a third, right? So that is what a direct variation is. Whatever the change in the x, however you're manipulating the x, the inputs, how they're changing, varying, then that same reflection happens in the output. Okay, now let's take a look at inverse variation. So for inverse variation, it comes of the form, I'll switch my color here, it comes of the form f of x equals our constant of variation, but this time our input is in the denominator, or 1 times 1 over x, right? So what this creates is different from this one. Again, just an input, just an output. Our input, though, happens to be in the denominator. It can be in the denominator of any fraction, but it's in the denominator. That's the key thing here. Maybe we highlight that as a piece of information. In denominator. Okay, that's what makes this a direct or an inverse variation versus a direct variation. So it's still, k is still our constant of variation, but look what we say about this one. This one we say y, or f of x, this really should be f of x. F of x varies inversely with x. This one over here, f of x varies directly with x, but now we're varying inversely with x, and the same thing can be said the other way. X varies inversely with y. What does that mean? Well, let's take a look at what we wrote here. As x increases, as our input increases, our output has to decrease. But because if you look at what's happening here, as we increase our output, right, if we increase our y value, this being in the denominator gets bigger, which actually makes this more of a decimal, which makes this smaller, right? This is decreasing overall. So as our denominator gets bigger, that means that we're dividing this up, and this gets smaller. So, and then vice versa, as we decrease x, our y has to increase. So these are, I don't want to use the word opposite, because inversely is the word that describes it better, but let's take a look at what these would look like then. So f of x equals 1 times k, or 1 times k, or 1 over x, which 1 then would be your constant of variation. Here's another form. We could have 2 times 1 over x. We could have 1/3 times 1 over x. We could have 3 over x, or we could have negative 3 over x. So that's what you're looking for, is that this x is the denominator, making these inverse variation. And again, you can still see your constant of variation. Sometimes your constant's in the numerator, right? Well, you can pull those out. That would just be 3 times 1 over x. All right, so it can be in both locations. Be okay with that. Let's see if we take one of these. Again, just like we said here, little equations. We can divide these up and solve for different parts. So if we can solve for the constant here, so if we take f of x equals 2 over x, go ahead and multiply that x to the other side. It could look like that. F of x times x equals 2. That's a little weird for us, but it can look like that. It could also, if we change f of x to y, it could look like y times x equals 2. Or x equals 2 over y. So lots of different forms for this inverse of variation. So let's take a look at what it does in our table. So if we look here, I'm going to plug into our inverse variation of f of x equals 2 divided by x. So I'm going to plug in 1. 2 divided by 1 is just 2. Oh, you can see the values there. I guess I forgot to erase them, so we'll write them in really quick. So we evaluated at 3 spots. Let's talk about then what happens, because this should be inversely proportional, meaning that if we double the input, right? So we went from 1 to 2, so we're doubling the input. Then if you look at the output, look what happens. It is cut in half. So this side is being cut in half while this side is doubling. And that's what inversely proportional means. So if we look at the next value that we plugged in, so if we go from 1 to a half, so in our input, we're cutting it in half, right? We're dividing it by 2. So we're going from 1 to 1/2. That's dividing by 2. Look at what happens to our output. So we start at 2, and it is going to double because it's inversely proportional. So if we decrease x, then y has to increase. Or if we increase x, then y has to decrease. That's the nature of this. Okay, let's stop there and we'll take a look at some examples.